Okay, I forgot to turn on the microphone on the last part. Please tell me when I do so. Now I'm going to teach you about mass midpoints. And we assume that we have given a mass density. Fx is given. That is a function of one variable, so we are looking at one thing. Say we want to find the mass midpoint of this one. So it will be, let's see if I can do this. Something like it. Because you see the mass of this varies along this line here. Let's find the mass midpoint. So we put our stick between A and B on the x-axis, and then I say this is the mass midpoint, and I call it C. So then I subdivide this part here, or I partition this in equidistance or equidistant segments, and I call this D, the length of this segment, dx left. And similarly, I partition this these segments here as dx right. Now let's take an arbitrary point here, x, y. Then I calculate the mass of this part of my stick, and so it'll be the integral from A to C, that is from here to here, and then it's my mass distribution. So you see, if I have a small part here, this is my delta XL, then this will weigh XI times delta X. But then again, you have this arm here, so it will give a torque around this point here in that direction. So you will get F of X, and then times this distance here, which will be x, it will be c minus x, and then dx. So this will be the moment around this point here of this part of the stick. And this should of course be equal to the moment of this part around this point. So this will be the integral then from C to B. And then it will be f of x times x minus so you see that you have the moment of the left-hand side, moment of the right-hand side, and they should be equal in order to have the equilibrium. So it's just a matter of rearranging this one, and you see here, C is a constant, which we're going to find. So I put this, or I split the integral. Let me start by doing this. I have the left-hand side, I have A, and then I have f of x times dx minus the integral from a to c, and then I have x times, and this is equal to the right hand side, you have c, and then you have f, or x times f of x minus then the integral from c to b. Now I collect the terms that contains c on the left hand side, and I put c outside the integral because it's a constant. So I get a to c, and then from c to b. And similarly, I put this on the other side, and I get the integral from a to c. And then the integral from c to b. Yeah. Now, this integral from a to c and c to b, this is simply the integral from a to b. And on the right-hand side, we get from a to b like this. Now this one here, what is that? The integral of f of x dx. So simply integrating the mass function from a to b, what do you then get? You get the total mass. So this is simply the mass of my stick here, if I use this. And then I divide by the mass, and then I get this formula for the mass midpoint. Let me continue with the mass midpoint for a plane field that is 2 dimensions. Mass midpoint for a plane field. going to do there is that I'm going to say I want to find the mass midpoint of this sheet here, and I'll find it in one direction, and then in the other direction. So, and where these two lines crosses, I have the mass midpoint. So you can say that if I want to find this mass midpoint, I consider it to be a one-dimensional interval in that direction, and this will give me this formula here. You have the total mass, and then you have the integral over your field, and then you should have x times your mass density, and similarly in the other direction you have y times f of x y. So this is simply the mass midpoint. And there will be exercises this afternoon where you're going to look at that. So let me quickly take you through the last example. I have f of x and y equals to x squared plus y squared. So this is my mass density function. And B is given by, or I should write here, in polar coordinates. It's given by the R function in the polar coordinates. They belong to this interval from 1 to 2, and it belongs to like this. We need a parametric representation for B, and then we need to determine the mass, and finally we need to determine the mass midpoint. So let me just sketch this area for you. So in the xy plane, you have that in polar coordinates, you have the radius 1, and you have the radius 2. Like this, and then the angle goes from 0 to pi half. So you have this area here, or this field here, and what you want to do is that you want to find the mass of this field here, and you want to find the mass midpoint. And the first thing you want to do is that you want to parameterize this area. So say take an arbitrary point. It has the angle D, and then it has, say, the R coordinate, which is U, then this point here will be u cosine v, u sine v. So this is simply the parametric representation, that is u cosine v, u sine v. And remember always to give the boundaries for your parameters. This is gamma pi half. The next thing I'm going to do is that I'm going to find the mass. I take here the composite function, which is, I just put it into my f function, which is x squared, that is u cosine v squared plus u sine v squared. And again, you use the fundamental relationship. This is equal to u squared. Then you need to find the Jacobi function. So you differentiate your parametric representation with respect to u. You get cosine v sine v. And then you differentiate this with respect to v. You get minus u sine v, and then u cosine v. So when you compute this, you get u cosine squared minus minus, that is plus u sine squared. So you end up with this result here. And this means that m is equal to the integral from 0 to pi half, and then the integral from 1 to 2 of your function for the parametric representation, which is u squared, times the Jacobi function, which is u, and then the uv. So the indefinite integral of this one is 1/3 u cubed, and the result is, if you put in all the, is times pi. I just write down this one. This is 1 divided by m, and then there's the integral from 0 to pi half, and the integral from 1 to 2. Now you need, in order, where did I put? Yeah, I have it over here. So you have 1 divided by m, and then you have your x value, and that's the x of your parametric representation, that is u times cosine v, and then you need your f function, which is still u squared, and you need your Jacobi. And if you compute all this, you get 248 divided by 75 pi. And this is approximately 1,05. And if you compute C2, you get exactly the same thing. You have to replace this by u sine v, but the result is the same. And then this is also. So the mass midpoint is 1, and then the mass midpoint is here. due to symmetry, it's okay that the C1 coordinate is equal to the C2 coordinate, but it is here. That's the last point. But you will have plenty of opportunity to exercise this afternoon. Okay. I just